Okay, we're going to be talking about events. Okay, I kind of went back and did a little bit more than what I missed today, just to make it complete. We talked earlier about events, so some of this is going to be a little bit of a repeat from what we've done before, and some of it's going to be the stuff that I missed today on Thursday. So we've gone over random experiments, talked about outcomes. We talked about the sample space is all the possible outcomes. You put them together in a single set. That's the sample space. What we're really interested in, though, is events. That's the main things that we're interested in, which are collections of outcomes. So when you perform an experiment, a random experiment, you can ask whether an outcome has happened or not. The language we use is whether it's occurred or not. And we want to know what's the probability excuse me, what's the probability of an event, which under our interpretation of probability we're doing would mean if you were to perform the experiment a large number of times, what would be the long-term relative frequency of the number of the number of trials where the event occurred divided by the number of total trials. So say you do an experiment 20,000 times and the event occurs in 3,000 of the trials, then the probability should be 3 over 20 or 15%. So that was the empirical approach to probability. So what we're going to do is define an event mathematically and then come up with a bunch of definitions. And this is a mathematical framework for understanding this. It's kind of independent of whatever interpretation you give to it, but it works for the different interpretations because it's kind of independent of how you think about the interpretations. Okay, so the mathematical definition of an event that we're going to take in, if you go and study probability a little bit further, you have to be a little bit more subtle than this, so I don't want a bunch of people making YouTube comments that I'm saying something not quite right. But for the purposes of this class, for our sample spaces, we're going to define an event in a sample space is just a collection or set of outcomes. So in other words, it's just a subset of the sample space. And we usually denote these E, F, and so on, E for event, or A, B, and C. So an example, roll a pair of dice, one possible event, the sum of the pips, so those are the dots on the dice, comes up 5. Notice this is a verbal description of an event. In other words, I'm not actually listing out all the outcomes, although I do here. Because the sample space is so small, I can actually list them all out. But in general, the sample space is going to have a lot of different outcomes in it. So usually events are defined by some verbal description or some mathematically verbal description. Another example, each die is a multiple of 3. So that's a verbal description. There's also a list of the outcomes. Notice for the verbal descriptions, the important part is for every possible outcome, I can tell whether it's in the event or not. I can tell whether the event has occurred or not. It's well defined. There's no ambiguity about that. So I can go to 1, 2 for event F. I go to 1, 2, and no, that's not in the event. I go to 3, 3. Yes, it is. So as long as the verbal description gives me a way to always know whether the outcome is in the event or not, that's okay. Another example, toss a coin 3 times. These are both examples we did earlier. One event, toss at least 2 heads. So there's going to be 4 outcomes in there. Each of those has at least 2 heads. Another event, toss exactly 2 heads, and that has 3 outcomes. So again, the language we use, this is probability language. If you perform a random experiment, and if the result of that trial of the random experiment is an outcome of the event E, we say E has occurred, or E occurs. The tense doesn't matter. Otherwise, E has not occurred. does not occur. There are two special events. These are kind of like the extreme cases. The whole sample space S we're going to call the certain event. So why are we calling it the certain event? Well, if you perform a random experiment, you're going to get an outcome. Since the sample space is all the outcomes, the sample space has to occur. It's guaranteed because it has all the possibilities. It's certain to occur. So it's the certain event. And then on the other hand, we have this funny looking symbol here, which some of you may have seen from algebra class or some other class before, if you've taken it. This is a symbol for the empty set in math, but we're going to call it the impossible event because we're framing everything in terms of probability language. And impossible means it can never occur. This is the set with no elements, so it's the event with no outcomes. So if you perform an experiment, doesn't matter what outcome you get. Is it in the event? Well, no, because nothing is in this event. So it's impossible for it to occur. And we'll see in a little bit when we define probability of event that the probability of the whole sample space is 1, probability of the impossible event is 0. 100%, 0%. Everything else is between those two extremes. Whoops, second. Okay, so question, how do we define the probability of an event? Okay, well, since an event consists of outcomes, and probabilities of outcomes can be interpreted as long-term relative frequencies, we're going to come across the following definition that seems to make sense. If E is in the event, we're going to define the probability of E to be the sum of the probabilities of all the events. So the probability of an event is the sum of the probabilities of all its outcomes. So this is the same sigma notation that we had before when I introduced sigma notation, except instead of having an index, I just gave this verbal description, but it's the same idea. Instead of saying sum from I equals 1 to n, over a certain index, this is just saying, which terms are going to make up the sum. Well, I'm going to add up the probability of x, where x ranges over all outcomes in E. So the number of terms in the sum is going to be the number of outcomes in E. So you immediately see that this definition satisfies the following. The probability always has to be between 0 and 1. Because, look at this. If you take the probability of the outcomes in the impossible event, so this would be the probability of the impossible event. Remember we said we would see that this is 0. Well, there's no terms to add up. If there's an empty sum, that has sum 0. So that's 0. If you take the entire sample space, you're adding up all the probabilities of all the events, and that was from our definition of probability function, that the sum of all the probabilities in a sample space had to be 1. That was one of our axioms. So this has to be 1, that has to be 0. Everything else is going to be in between. Every event either has no outcomes, or all outcomes, or something in between. So if it's something in between, you're certainly adding up more terms than over here, and less terms, or equal to terms than over there. So the probability then has to be between 0 and 1. Example, roll a pair of fair dice. We define E5. You could do this for 2, 3, 4, up to 12. The sum of the pips is 5. So we saw that this was had 4 outcomes. And so by the definition of the probability of the event, this is the probability of 1, 4 plus probability of getting 2, 3 plus probability 3, 2, probability 4, 1. Since these are all equally likely outcomes, so we're assuming they're fair dice, so you have to be told they're fair. Equally likely outcomes, each of these has probability 1/36, so altogether probability 4/36. Next example, toss a fair coin 3 times. Okay, so this is one that we were just looking at earlier. There's 4 outcomes here. Again, since they're equally likely, they each have probability 1/8 because there's 8 outcomes in the sample space. So probability 4/8, and exactly 2 heads since there's 3 outcomes, each probability 1/8. The probability of that event is 3/8. So, do you notice a pattern with these examples? You should. What's going on here is, in the case of equally likely outcomes, counting probabilities reduces to counting problems. Now, in general, if you just have to count how many ways you can do something or how many things there are in something, that's going to be a little bit easier problem than trying to find a probability just in general. I don't mean to say that counting is easy. Anything from it is anybody who's taken a combinatorics class knows. But for us, the types of counting we're going to be doing are going to be pretty straightforward. So reducing the problem of computing a probability to the problem of counting up how many ways to do something or how many things there are is going to make the problem simpler. Excuse me. So another way to say this, and you're going to prove this in just a second here. If S is a sample space with equally likely outcomes, just like we had with tossing the coin 3 times and rolling the fair dice, if you have an event in a sample space with equally likely outcomes, it's a nice little formula for the probability of an event. It's simply the number of outcomes in the event divided by the total number of outcomes. So I've used the pound symbol here to stand for number of outcomes. So this is number of outcomes in E divided by number of outcomes in S. There's 2 other main notations that you might see for this cardinality. It's called the cardinality of a set. You might see little n. So if you see little n, like a little n of E, that would be number of elements in E. Or the absolute value symbol. Just like the absolute value of a number, sometimes you put the absolute value around a set. That is taken to mean the cardinality, or the number of outcomes in there. So why is this true? We went through some examples. Seems like it should be really obvious. Well, math people are really famous for taking something that seems really obvious and making it mumbo jumbo. So let's see how well we can do that. So here's how the argument runs. The probability of E, by definition, is the sum of the probabilities of all its outcomes, P of x over all outcomes x and E. But here's the key point. If they're all equally likely outcomes, we had a previous result that said that the probability of each of the outcomes was 1 divided by the number of outcomes in the sample space. Well, how many things are in the sample space? That's pound of S. So this sum, we're really adding up 1 over number of S, where the x ranges over the same thing, so ranges over all the outcomes in E. So this has nothing to do with x. That's the key thing here. We've kind of removed the dummy variable, removed the index. Here there was an x, here there's no x. So all this is saying is just add up 1 over number of things in S a certain number of times. We just need to know how many terms. So how many terms are there? Well, there's going to be 1 term for each outcome in E. In other words, there's going to be number of E terms. Well, what happens when you add a number to itself with a certain number of terms? Well, repeated addition, that's multiplication. So it's number of E times 1 over number of S. So number in E divided by number in S. And that proves what we just did. So we're going to go some more with events and talk about unions, intersections, and stuff like that in the next video. Okay.